In this video, we're going to learn another technique for solving systems of linear equations. This time we're going to be using matrix inverses. So we're going to be solving a matrix equation using inverses. So before we get to that, we want to see why or how matrix multiplication can be used to turn our system of equations into a matrix equation, so an equation involving matrices. So let's just think about this system here. So x minus y equals 5, and 2x minus 5y is equal to 4. So what I want to do is start writing this using matrices. So the easiest way is to turn the system into a matrix equation with two matrices that are both 2 by 1 matrices. So they have 2 rows, but only 1 column. Okay, clearly this is equivalent to the above equation set because this number needs to equal this number and this number needs to equal this number in order for this matrix equation to be true. So now I want to rewrite this a bit differently. So I'm going to rewrite it. So this is 1 times x plus negative 1 times y, and this is 2 times x plus negative 5 times y. Okay, this 5, 4 is still the same on the right hand side. So you can see that I'm multiplying by xy, or there's x and y here timesing some numbers. We can actually write this using matrix multiplication. So this is actually the matrix 1, negative 1, 2, negative 5 times the matrix xy as a column matrix. Okay, so notice here I have a 2 by 2 matrix multiplied by a 2 by 1 matrix. So this multiplication is defined because those are the two inner 2's are the same. And we're going to get a 2 by 1 matrix, okay, which is what we wanted because that's what we had before, right? All of these are 2 by 1's. So now think about it. If I tried to undo this, let's say, I would take this row times this column, okay, that is this entry, right? 1 times x plus negative 1 times y. And then I can do the same thing with this row, use the same column. That gives me this entry here, 2 times x plus negative 5 times y. So what I've done is I've rewritten my system of equations as a matrix A times what we call a matrix X and equal to a matrix B. Now notice that A, this is our coefficient side. So it's the coefficients of our initial system, right? 1, negative 1, 2, negative 5. So we would call that the coefficient side of our augmented matrix. So here we call it the coefficient matrix. Okay, B is a column matrix. It's a column matrix containing our sort of answers. Okay, so we call it the constant matrix because it has the constants in it. Okay, but it's a column matrix. Now X is our variable matrix. So it's a matrix that contains our variables. Okay, and it's also a column matrix. So it just has the variables down the column. And it turns out that you can always write a system of equations using a matrix equation of this form. Okay, so the coefficient matrix times the variable matrix, that's a column, and equal to the constant matrix, which is also a column. So what we're going to try to do is solve a matrix equation that looks like this, because that's going to be equivalent to solving our system of linear equations. So before we do that, let's just talk about in detail how we might solve a regular old equation with just numbers that looks similar. So I have a number times my variable x equals some other number. Okay, so we have A times X equals B. So if I wanted to solve for X, probably the thing you're thinking is I should divide both sides by A. So if I divide by A, then the A's cancel over here, I get X by itself. But instead of dividing by A, what we could do is actually multiply by 1 over A. Okay, this is the inverse of the number A. Now, why do I want to do that? Because our multiplication is what we call associative. So I can move the brackets around and I could do 1 over A times A and then times X. I'm going to put my 1 over A actually on this side. So again, why did I care? Well, what is 1 over A times A? Well, that's 1. Okay, so that's going to be 1 times X equals 1 over A times B. And what's special about the number 1 is that when I multiply by it, I don't change this number X. Okay, so then instead of writing 1 times X, I can just write X. Okay, it equals 1 over A times B. So that is graphically, okay, so a very graphic way of solving this. So we use the inverse of A, and we also use this number 1, okay, which we might call the identity for numbers. So I can multiply by it and nothing happens. When we do this for matrix equation of the form AX equals B, it's going to look a lot similar. Okay, so I'm going to have A times X equals B. So I want to get rid of the A, so I want to solve for X. So this is why I wanted to write it as 1 over A instead of divide by A, because we don't have a divides for matrices. But we do have an inverse. So what I can do is multiply by the inverse. So assuming that A inverse exists. Okay, if A inverse exists, I can multiply. Now I want to be careful here. Because the order I do what things matters, I want to multiply on the left. Right? So that the A inverse and the A are next to each other, which means that I have to multiply on the left over here as well. So I can't do what I did up here, where I just multiplied by 1 over A, and I didn't care what side. That is because multiplication for numbers is commutative. So it doesn't matter what order you do it in, but for matrices it does. So if I multiply on the left on one side by a matrix, I have to also on the other side multiply on the left. So we do that, and then matrix multiplication is also associative, so I can't change the order, but I can move the brackets around. Okay, so I can do the inverse times A before I multiply by X. So do we know what A inverse times A is? Well, yeah, we do. Remember, inverses, the meaning of inverse is that when you multiply them, you get the identity matrix. Okay, so the identity matrix of the same size as A. Now, what happens when I take the identity matrix times the matrix? I just get the regular matrix back. So we see that we've solved for X, but we wanted to use the inverse and then equal to, we get the identity when we do the multiplication. Same idea, so we're using the inverse of the number A, and then we do that so that we get the number 1. Because we know 1 times a number is just a number. Okay, so that's the same for matrices. So, if the matrix A has an inverse, then the solution of the matrix equation AX equals B is going to be X equals A inverse times B. So this always is how you can solve for the solution for a matrix equation of that form. So let's do an example. So suppose we want to solve this system of equations. So you could row reduce, okay, you could augment and row reduce. We're going to use matrix inverses. So the first thing I'm going to do, is write this as a matrix equation. Okay, so we should be able to write it as A times X equals B. So remember, A is our coefficient matrix. So that's going to be 3, 3, 4, 5. Okay, the X is our column matrix with our variables in it. So that's going to be a column containing X and Y. The equal stays where it is. And then I have a column with the constants, so negative 9 and 12. Okay, so this is my A, this is my X, and this is my B. So what we want to do is we need A inverse. Okay, now you can use, because A is a 2 by 2 matrix, you could use the formula. I think I'm going to use row reduction just to practice that method. But again, you could use the formula to find the inverse if you want. So let's find A inverse. So I'm going to augment A on one side and the identity of the same size on the other side. Okay, and then I want to row reduce. So I first want to take row 1 and divide it by 3. So I'm going to have 1, 1, 1/3, and 0. Okay, my next step is to do row 2 minus 4 of row 1. So that's 1, 1, 1/3, 0. Now the 4 is going to be a 0. Now I have 5 minus 4 times 1, so that's 1. 0 minus 4 times 1/3 is going to be negative 4/3. 1 minus 0 is 1. Okay, now I'm pivoting around this 1 here. So I want to make the 1 above it a 0, so I'm going to do row 1 minus row 2. Now I have the identity on the left. Okay, so I have 1/3 minus negative 4/3, so that's plus 4/3, so that's going to be 5/3. And then 0 minus 1 is minus 1. Okay, so now I have the identity over here, so this part is going to be my inverse matrix. So we know that A inverse is going to be 5 over 3, negative 1, negative 4 over 3, and 1. So if we use that, so we know that X is going to be the inverse times B. So now I just want to multiply this inverse times our B matrix, which was negative 9, 12. So I have a 2 by 2 multiplied by a 2 by 1. Okay, these inner 2's are the same, so I can do the multiplication, and we're going to get a 2 by 1. So I take this row times this column. That gives me my first entry. So it's 5/3 times negative 9 plus negative 1 times 12. And then I do this row times that column to get my next entry. So that's negative 4/3 times negative 9 plus 1 times 12. So if you simplify, this is going to be negative 15 minus 12. Here I'm going to have 12 plus 12. So I get negative 27 and 24 in my matrix. So we remember that X, which is xy, little x and little y, this should be equal to negative 27 and 24. So that means our solution is going to be little x, it has to be negative 27, and little y has to be 24. Now notice, because if the inverse exists, then I'm going to be able to always do the multiplication. So A inverse times B. So that means that I always get a unique solution for x. Okay, so that means if my system, my initial system, has no solution or infinitely many solution, I shouldn't be able to find the inverse. So remember that this method only works if the matrix has an inverse. So this is going to tell us, maybe I want to write this down. Okay, so this means that the system equivalent to matrix equation A times x equals B has a unique solution because you're able to solve for it, because you're able to find x. So if your system does not have a unique solution, it means that you will not be able to find an inverse. Okay, so that means that your coefficient matrix does not have an inverse. Okay, let's try a few more. So here, they tell us that the inverse of this matrix A is this matrix A inverse. So we don't need to check that. We don't need to find the inverse of A. They're giving it to us. Okay, so hopefully that's going to be useful. So what I would want to do to solve these systems is write them as a matrix equation. So this is 4, -2, 3, 8, -3, 5, 7, -2, 4. And then I'd have to multiply by the variables, so x, y, z. And that should be equal to 1, 4, 5. Okay, this is A times x equals B. And now if you notice, this matrix here is this matrix here. Right? It's identical. So that means that I know the inverse. So I can solve my x is going to be the inverse times b. So I just have to do this multiplication. So I take the inverse matrix and I multiply by my b, which is 1, 4, 5. So when I do that, -2 times 1, -2, plus 8 minus 5 is my first entry. And then I have 3 minus 20 plus 20. And then I have 5 minus 24 plus 20. So I'm getting 1, 3, and 1. Okay, so that means that my solution should be x equals 1, y equals 3, z equals 1. So notice if we had the inverse, it's much, much faster to use the matrix equation form to find the solution. Okay, now what about the next one? So if I again put this into a matrix equation, it's 4, -2, 3, 8, -3, 5, 7, -2, 4, times the variables as a column should equal 4, 7, 6. Now I've seen this before. That's the exact same as the matrix up above. Okay, so this is still matrix A. Okay, X, and now I'm going to call this B1. Or actually maybe, well, whatever, that's fine, B1. So I have a new B matrix, but everything else is the same. So my solution, again, I just have to multiply my inverse by my new B. Okay, so the inverse is -2, 2, -1, 3, -5, 4, 5, -6, 4. Now I'm multiplying by 4, 7, 6. So I have -8 plus 14 minus 6. And then I have 12 minus 35 plus 24. and then 20 minus 42 plus 24. And if I simplify that, I think I get 0, 1, 2. So that means that my solution here is x equals 0, y equals 1, z equals 2. And again, you could check each of these in your original equations and make sure that they work. Okay, what about this last one? So this one does look different. Okay, so if I do write this one out, it's going to be -2 to -1, 3, -5, 4, 5, -6, 4, times my variables x, y, and z, and it's equal to the column matrix 1, 0, 2. So this one looks very different. However, I have seen this matrix before. Okay, it is the inverse matrix. Right? It looks just like that. So this is A inverse times X equals, let's call it B2, so some other system. Okay, so what I want, so I should be able to solve this. So X, it should be the inverse of my A times my B2. Okay, now A inverse, this is just A. Okay, so if A inverse is the, so if A inverse, okay, is the inverse of A, then the inverse of this is A. Okay, so they're inverses of each other. So I just have to multiply by A this time instead of A inverse. So that's going to be 4, -2, 3, 8, -3, 5, 7, -2, 4. And I want to multiply by 1, 0, 2. Okay, so if I do that, I'm going to go down here. I get 4 plus 0 plus 6, 8 plus 0 plus 10, 7 plus 0 plus 8. So I get 10, 18, and 15. Okay, so my solution here is x equals 10, y equals 18, z equals 15. Okay, so these, because the inverse existed, all three of these systems, because their coefficient matrices were either A or A inverse, they all have a unique solution, no matter what the B matrix is. Okay, so knowing the inverse matrix, so if they give you the inverse matrix, definitely this is going to be the fastest way to solve your system. Okay.